I've won again.
We set out to develop a robotic system capable of playing the game Connect 4 against a human opponent. In Connect 4, two players compete by taking turns dropping chips into a game board. The objective of the game is to arrange 4 tokens of your color in a continuous line, vertically, horizontally, or diagonally. Our system is capable of seeing and interpreting the game board, locating and picking up tokens, and finally deciding upon and executing an advantageous move. The first step in our system was to identify the state of the game in real time using a camera. We chose to use a wide-angle lens so the camera could be mounted on the arm and still see the entire board. To determine the game state, we first used a union find algorithm to isolate 35 non-blue regions within a single blue section of the image. Once we had these regions, we could use a ransack to test a homography which would map each identified blob to the corresponding location on the game board. Ransack allowed us to compute a homography even when some non-blue regions were not detected by union find. After that, it was a simple matter of determining if each blob contained enough red or yellow pixels to be considered occupied, and if so, by which player. We also knew that each legal move would add only a single piece to the previous state in 1 of 7 positions. We used this fact to verify that the board was correct, determine if our opponent had made a move, and determine if our robot had misplaced a chip. To pick up a token, the arm used a simple 2-step process. First, it assumed a configuration that allowed its arm-mounted camera to look at tokens on the table. Then, these tokens were identified using a union find, and their location in the real world was computed from a known homography. Finally, their angle was roughly determined using the coordinates of a set of 4 pixels at maximum and minimum x and y coordinates. Connect 4 is a sum-zero game. That is, every time one player wins, the other loses. Because of this, we were able to use a minimax algorithm to determine the best possible moves. Minimax works by expanding every possible move to a certain depth and alternating between choosing our best move and the opponent's best move, which is usually the worst scenario for us. In this example, we can see each of the 7 possible moves for the red player. For each of these moves, the opponent's possible moves are enumerated. This process is repeated as many times as desired. We decided to use a depth of 6 because this proved to be a nice balance between intelligence and computation time. After examining all possibilities in this tree, the algorithm assigns each a score, and assuming the opponent chooses its best possible moves, the algorithm will select a move that minimizes the opponent's odds of winning. After implementing each part of our system, we extensively tested it to make sure that our robot was as robust to failure as possible. We also wanted to make our game engaging to the user by creating a unique visual interface and adding voice sound effects to accompany gameplay.
I've won again.
Overall, we were excited about the outcome of our project, and we received very positive feedback from everyone who had played against it.